All right. So starting off on question 3, just for reference, if you guys want to watching the recording right now, I already explained to people in the live, go to the description of this video, and there will be a link to what you're seeing. If it'll update. There we go. On the screen, there'll be a link to this. We are going over the one that's highlighted. It's called Manny Gomez Old Notes, Wrong Answer Rationale. Let's go ahead and open it up. Click here, download it, so you'll have it your own. And we are on 3. The last episode we went over 1 and 2, so I'm gonna go ahead and share that. All right, so again, going with the same strategy we had last time. When you see a problem, personally what I did was trust that what they're giving here on the top is safe. They're not gonna do any tricky stuff. Everything there is meant to be there, and it's basically setting up the circuit. So what I did was I would see the question they asked. So assuming the fragment below, which 3 code fragments would produce the circuit illustrated? So you can see I circled underlined 3, so we know what we're looking for. And what I normally do is I immediately hop to the bottom. And I would go from the bottom and work my way up to see what's going on. So once you get familiar with these things, you start to be able to have a picture in your mind what's going on in the code. So starting off on F, qc.h imp reg. So a Hadamard gate is being placed on what's named imp reg. So now we go back up to the top and we see what is imp reg. Imp reg is established as, it's a quantum circuit. Let's see here. So its name is imp, and then there's 2 of it. And then going 1 line below, something very, very similar, ancilla, and that's a quantum register. So both of them are quantum registers. I might have misspoken. So both of them are quantum registers. The first one has 2. I might as well mark this up. The first one has 2. It's created 2, and they're named imp. So if we look there and we follow down here, we can see they're first named imp 0 and imp 1. So that's the naming convention that automatically happens when you set up multiple ones. Notice it didn't explicitly state imp 0 and imp 1 is being set up. So that's what happens when you use that type of syntax. So then what happened after that? So these 2 are set up. These 2 are set up with this first one. Ancilla, this one right here, is set up with the second one right here. So ancilla is a quantum register. 1 qubit is being set up, and its name is ants. So again, we see that reflected here, ants, and then automatically comes with the prefix or the end of 0. So if we go back down here, let's see if I can get them all in frame. On F, what's happening? A Hadamard is placed on the entirety of imp reg. So again, looking up here, there's 2. So 1 is placed on each of them. And then we have another Hadamard being placed on imp reg. And then an X gate being placed on the entirety of ancilla, and then it's being drawn. So an easy thing you can do to see easy questions, the last point is qc.draw, so it's being drawn. And sometimes what they do is the answer is missing a very simple draw command. So what I would do is I would look at draw and make sure they all have the draw command. So they all do, and that's something small, but that's an easy way to find the answer, especially when you're under a time crunch. So on this one, what happens? There's a Hadamard placed on imp reg, there's a Hadamard placed on imp reg, and then an X placed on ancilla. And that ends up, if we look on the right side, it would look like this, and that is not what we're looking for here. It would actually give us an extra set of Hadamards right here that we're not looking for. So that's why F is not the answer. So again, going up, a Hadamard is placed on, so here we see our first encounter of this syntax right here. A Hadamard is placed on the first bit of imp reg. And then a Hadamard is placed on the second bit of imp reg, an X on the first bit of ancilla, and then it's drawn. So with this one, we can kind of see some red flags. So imp reg 2 does not exist. We can look at it and see that it starts at 0, so it's just not placed. And again, we look at the justification here. Ancilla 1 also doesn't exist. So look at here. and we go back to the top, and we notice that it actually begins with ancilla 0. So getting used to the naming convention is something you'll want to do, because it'll really help, and it's going to come up later in the same problem and other ones as well. So those two just don't exist, which is why E is not the answer. D we can skip over because we know it's correct. C, why is it not correct? Oh, excuse my language here, but on the left you'll see it's highlighted in orange. Notice the BS syntax that's tripped me up in the past. So sometimes I learn things based off of like textbook rules, and sometimes while studying, I've gotten it wrong so many times that negative emotion that that's associated with it is what makes me remember it. So like this is one of those times where it's like, all right, like 0 to 2 doesn't mean from the 0th to the second qubit or second bit. It actually means from the 0th to the first. So what you actually do is you take the final one and you subtract 1. And here you can see me re-explaining it. But it would be this one gets placed at the 0th, but it actually goes until the first. So for C, it's incorrect. Again, because the BS syntax, you just learn to learn that's how it's worked or it's done. So it wouldn't cover it because 1 minus 1 would be 0. So this would actually be from the 0th qubit to the 0th qubit, which would only be 1. So then from that mistake, we've learned that this would cover from the 0th to the first, which is what we have here, 0th first. So right here, you'll learn the syntax. This brackets means you want that element multiple times. So we have the Hadamard placed on the 0th one, and then we have it placed on the first. Again, keeping in mind that that's how the syntax works. And then we have an X placed on the 0th qubit of the ancilla. So we have this right here. So that's why B is correct. For D, let's see here. So we have a Hadamard placed on the 0th of the impreg, so that's correct. A Hadamard placed on the first qubit, so that's correct. And then an X placed on the ancilla on the 0th qubit, so that's correct. So if we look, D is doing a long version of B. So it has an extra command because it's doing what's done in 1 step in B in 2 steps in D. And then A, let's see here. Oh, okay, so with this example, they try to teach you something with all the examples. And this one's showing you how different things can be placed. So this one places a Hadamard on the entirety of impreg. It places an X on the entirety of ancilla. And it places, and it draws it. Wow, we are already 13 minutes in. Okay, so I'll finish this one up and then the one after it. Okay, so that's how we can see A, B, and D are correct. F places it twice, so we wouldn't want that. E uses syntax of bits that don't exist because they start at the 0th one. So that's what they try to show you with E, or teach you with E. And then C has that syntax again. So again, like we said in the first episode, and we'll keep saying, a big thing in this exam is the syntax. Of course, you know, it's just nature of the beast of how Qiskit works, and it's important to understand the main ideas and what things are doing, but you still need to know what needs brackets, what needs parentheses, and all those things. So this question tries teaching you and making you remember the different syntax of how to place different gates. Okay, 4. Given an empty quantum circuit object, QC, with 3 qubits and 3 classical bits, which one of these code fragments would create this circuit? So again, what I learned to do after looking at this stuff for a while is I would ignore what's given. So this is what's given. I consider that what's given. This is what's given. And this would be what's given for this one. And I would immediately jump down to the questions. And most of the time, the questions have immediate red flags. So for this one, I'm going to switch to the computer here. And one of the main things we want to learn here is how to think in order to pass the exam. So when you have a question, what do you do? And right now, this question is asking us about the quantum circuit object. So what do? Is we type in quantum circuit, Qiskit API to get more information on it. And here we see it. Let's see here. Creates a new circuit, and let's see if they have examples. Let's see here. For example, here we go. Quantum circuit 4 creates a quantum circuit with 4 qubits. Quantum circuit 4.3 creates a quantum circuit with 4 qubits and 3 classical bits. And actually looking at this question, we notice that the question options, the answer options, are actually on qc.measure. So going back, we'll type in qc.measure Qiskit API. Because we have questions about it and we're trying to learn. So quantum circuit, let's see here, Control F to search the page. We'll look for the measure command. So here we have an example of it. Most of the time farther down, here we go. In the documentation, we'll see examples of it. Here we go, measure quantum bit info into classical bit tuples. So here we can click this, open a new page, and see a little more about what it does. Attach measure instruction, measure, and then we also have this one, which is relevant to this question, measure all. I wouldn't get too hung up on learning all of these. There are specific ones, like these chasm ones, converting it from Qiskit to quantum assembly that you'll pick up on that are more important than others. And here's the measure all one. So going back to the document camera, we see this question. So it says, which one of these code fragments would create this circuit? So starting from the bottom, qc.measure 0, 1, 2. So I know this because I've looked at it so much. So I guess the main thing we should do for this type of example is go down to the bottom and see what the rationale for it is. So dot measure only takes in 2 arguments. So if you look at this dot measure, it has 3 arguments, which would be an invalid input. So that's why D is incorrect. For C, let's see here, qc.measure all. This one took me a while to learn. I actually had to ask the Slack, questions about it. On the Slack, there's a certification exam channel. I'd really recommend asking questions in there if you do have any. The Slack link is in the main hub document that'll be attached or linked, pasted in the comments of the description of the video. So qc.measure.all is invalid because it adds an unnecessary additional classical register. And when you go into the documentation of measure.all, you'll notice that it adds another classical bit. So this one, instead of saying 3 right here, it would say 4, which is why C is incorrect. And then for B, QC measure, so it creates 2 here, it creates 2 here, and it creates 2 here. But again, for the same reason as D, measure only has 2 input arguments. So that is also why B is incorrect. Measure only takes in 2 arguments, yep. And then A, you get to learn the syntax. So brackets means we want this element in these locations. So right here it's saying qc.measure. We want the measures to originate at 0, 1, and 2, and we want them to measure to the classical bits of 0, 1, and 2. So they're actually paired like this, and I'll color them so it's easier to see. This one goes with this one. This one goes with this one, and this one goes with this one. And then to make it even better, I'll do this, this, and this. And this is the green one. This is the orange one. This is the pink one. So those are actually what they represent. That is all the time we have for today for the teaching of them. So we did 2 and 3 and 4 today, and we actually have a guest speaker today. She is the program director of QubitXQubit, Rachel Zuckerman, and she has a presentation that I have. Yeah, feel free. It's videoing right here, so if you stand here, give me 1 second though. Let me see.
Who's all there? Can folks introduce themselves?
Yeah.
Like why they're interested in quantum?
Not many people here. Keenan and Sergio. Yeah, go ahead and say in the chat why you're interested in quantum. I'll put her presentation on. Oh.
I'll be quick too.
No, that's fine. external input.
Oh, this on Discord.
Mm-hmm.
Your Discord is
Mm-hmm. Oh yeah.
so modern.
Yeah. And if you're free to use the mouse and whatever. Oh, here's the mic. Just put it here.
Oh my god, this is so fancy. Hi guys. Cool. We'll jump right in. How do I see the chat? Why are you all interested in quantum?
I'll put the chat in this monitor so it doesn't display on the thing. And then covering it up.
This is the most like 2021 thing I've ever done in my life.
Yeah.
Can I see the screen?
They're typing right here. So when they come up, it'll be.
Cool. All right, I will jump in. They can see the slides?
I think so. Hold on.
Or is it that
I just
screen?
couldn't see.
Is that the screen? Sergio, I hear that all the time. Everyone's like, quantum mechanics is just like really cool and a hobby of mine. Awesome. Cool. All right, I'll jump in. I know it's Friday night and folks probably want to either do something fun or at least take a break from staring at a screen. So I'm Rachel. I am the program director for QubitXQubit. We are a nonprofit 501c3 quantum education organization. So really one of the first of its kind organizations in the world committed exclusively to expanding access to quantum education. So as I'm sure your own experiences reflect, most people haven't had the opportunity to have formal training in quantum computing for sure, sometimes even quantum mechanics. These have been topics that are predominantly reserved for PhD level work or advanced graduate school work, and with the changing environment and the exciting potential of quantum computing and other quantum information science and engineering technologies, there's a real need to expand access to quality educational opportunities. So I'll just cruise through this very quickly. But generally speaking, so our mission is very much so a social impact mission. We really believe that expanding access to quantum education, just like a decade ago expanding access to computer science education, is a social justice issue, a social equity issue that quantum education is as well. So we work really hard to make our programs either free or low cost, really an emphasis on equity and ensuring that the future quantum workforce is diverse and inclusive, which it's really exciting with quantum technologies being a new and emerging field and a race to develop a workforce very quickly. We have an opportunity to build the workforce from the ground up, and we are trying to do everything in our power to seize that opportunity. So just briefly, we have a few kind of key mission components. We focus on early access to quantum education, so we work a lot with high school students, K-12 students, and early undergraduates, although we have programs kind of across the spectrum, and we're working to develop new programs. We focus on increasing diversity in the field and training the next generation of quantum leaders like yourselves. We have a pretty rock star board that we're really proud of advisors, really the leading names in the field. So we've got Dr. Scott Aronson, Umesh Vazirani, who designed the Vazirani algorithm, James Whitfield at Dartmouth, Will Oliver at MIT. You can see on the screen, but we're really proud to have a pretty incredible set of experts who help guide our work. Yeah, we do, like I said, work kind of across the spectrum of age groups. We've done a lot of K-12, including like middle school camps where we have middle school students coding their first single qubit quantum circuits. We have a two-year college program, so we're working on community college programming, hoping to develop more four-year programming for college students like yourselves, and then starting to think about what workforce upskilling programs would look like for someone who, for instance, is a software engineer and just wants to learn, based on their knowledge of Python, Qiskit syntax, and start being able to contribute to quantum algorithm development, things like that. Oop, I keep going backwards. So in the last 2 years, we've really only been around for about 1.5 years. I started my job literally a year ago, October 2021. In that time, we've trained 15,000 students. So we are the largest quantum education organization in the world. We've had students from over 125 countries, all 50 states, and again, more than 50% from backgrounds underrepresented in STEM. And we continue to hear how exposure to quantum can be really a life-changing opportunity. So this fun quote from a high school senior who was like convinced he wanted to be an electrical engineer, and after taking our course last year knew he wanted to become a quantum engineer, which is, you know, in high school not something you would even know is a job that you could hold. So we're really proud of stories like that. This is more so just kind of like our pitch to funders and prospective partners, but our outcomes have been pretty incredible. 99% of students, high school students, are more likely to take a STEM course in college after participating in our programs. They develop real skills in quantum, they're interested in studying quantum further, and many are even interested in pursuing careers in quantum. So I think quantum computing is really cool, especially for young students. I keep describing it as like you basically can get students, especially high school students, to eat all of their vegetables, and it's like packaged like a shiny little cupcake. Like you have to do some pretty advanced math, you have to learn how to code, you have to learn physics, you have to learn engineering principles, all of these really, really important fundamental STEM topics, but it's like all within the context and application of quantum computing, which is awesome, obviously. So we've seen great results from that. Our students are awesome. This is Jade. She started literally within the first 3 days of her freshman year at the University of Maryland, one of the leading quantum universities in the country. She started their quantum computing club and got 40 students interested right away, so she's pretty awesome. Emil from Canada, and then yeah, some of our other students. I won't get too much into our program design. We've done a lot of virtual programs so far, mostly because programs have been done during COVID. We are working on new programs, like I mentioned. I would love ideas. We're hoping to launch an undergraduate quantum computing network, so we would be able to provide resources to students like yourselves from across the country who are looking to learn quantum computing, in part through convening their quantum computing clubs. So there used to be very, very few quantum computing clubs. It seems like there are new ones every single day, and we would love to be able to organize like panels with researchers at the US national labs who are doing some of the most cutting edge research in quantum information science, be able to do panels and discussions with folks who've gotten internships in quantum computing. You can learn a little bit about their experience and how they went about the internship search. I should have mentioned IBM is one of our primary partners, so they have funded several of our programs and helped make it possible for our programs to be free and open to students all over the world. So I'm not sure, yeah, this is one of our course curricula. I'm not sure how well you can see it, but we have a 1-year Introduction to Quantum Computing course. Last year it was open to students of all age levels. This year it's specifically for high school students. We kind of do everything through the full spectrum of introductory linear algebra. We don't have prerequisites, so students learn to code Python for the first time with us in many cases. They ultimately will get through Grover's algorithm, quantum key distribution, kind of your basic set of algorithms, VQE and near term. Nice. Yeah, now maybe you can see it better. Grover's algorithm, VQE and QAOA, so near-term quantum algorithms, discussing applications in quantum chemistry, quantum finance. So it's a pretty cool curriculum, first of its kind. This is really just kind of a feel-good, kind of fun thing, but our course was for students, and last year, in part because of COVID and the pandemic, a lot of parents ended up taking the course with their students. So they would log on to their big screen at home, and then their family would learn quantum computing together, and some of their parents even got the certificates that students got for completing the course. So we do a lot of education advocacy. This presentation is from a panel that I spoke on earlier this week for IEEE, the International Engineering Organization. So these are kind of the takeaways that we share with policymakers and leaders in the field. So there's a ton of interest, as you all demonstrate as well. Quantum doesn't have to be inaccessible just because it hasn't been taught at the K-12 level or with younger students in the past doesn't mean that has to be the case. There are accessible introductory ways to introduce this material in a way that sets students up for success and will be really, really crucial to expanding diversity in the pipeline and just scaling up the amount of talent and folks with quantum know-how that we need in the next 3 to 5 years, maybe less time. And yep, quantum computing can increase students' excitement about STEM. If we want to expand diversity in the field, we have to start early. We cannot start at the PhD level when there's already been a lot of sorting of students that has happened. And there are a lot of gaps in the quantum pipeline. So you all have experienced that, no doubt, but there are not yet widespread access to early learning opportunities. There are not yet really extensive internship networks. Internship opportunities are growing, but they're still often for students with a PhD. And so we're working to develop programs and connections in the ecosystem that reduce the gaps in the pipeline. These are some of our students. They're really incredible. And I won't bore you with some of the questions we're trying to answer, but there are a lot of challenges. This is a really exciting but new space. And so we're trying to figure out how do we improve outreach? How do we, when we think about Chicago Public Schools, what does it look like to integrate some element of quantum education into a high school in CPS? We're still figuring out new curriculum design models. You know, quantum is super interdisciplinary. You have to, again, have strong background in math. You have to be able to program. Maybe you're doing some work with hardware, so you have engineering credentials, understanding quantum physics, which is a leap in and of itself. So there's a lot of new approaches to how we're developing curriculum for students at different levels and based on the specialized path they want to go down. So obviously if you're interested in cybersecurity, that's a different skill set you need than developing the next quantum computer and focusing on hardware or qubit design or chip design, all different skill sets with different specialized training required. And we're always trying to get our programs funded. So funding is definitely still a challenge. And yeah, that's my information. I would be happy to do anything I can to support you all. I should have mentioned I live in Chicago, so our team is remote. We're kind of all over the country. We've got hubs in New York and Boston near MIT and kind of in several other cities too, but I'm here in Chicago and I love meeting students who are interested in quantum and happy to be a resource if there's anything I can help with. And happy to take any questions if you have them in the chat. Or out here. Sergio said, I love your mission to open up quantum computing to individuals in underserved communities. Are there any volunteer opportunities? That's a great question. Yes, definitely. We can talk about ways to get involved. It's not a paid opportunity, but for folks who do have a background in quantum, for every program we have teaching assistants. So if you have any interest in teaching high school students or fellow undergraduates, that's always something we're looking at. And we're trying to build out curriculum development and other volunteer opportunities. It's kind of hard just while we're figuring out We have a very small team. I'll just say it this way. We have a very small team, and so I'm trying to figure out a volunteer management structure that will work and give everyone a good opportunity. But if you're interested in curriculum development, like we'll be doing a program in New York City in January that takes our virtual curriculum in person, and so we'll be doing it with middle school students and high school students. So we're trying to come up with what are some like hands-on activities that young students without a lot of background could do. So can we like construct a 3D quantum computer that students can take apart and understand the elements of quantum hardware? Or can we create like a circuit design or chip design hands-on activity? So those are the types of things that, if they're fun and interesting for you to think about, we're always looking for brain power and creative people who might be interested. Are there currently any available resources for undergraduate students? So we've done several programs for undergraduate students. We offer live courses, so we don't have like curriculums that we just post and make available, because we think live instruction is really, really important to student learning. So I'll make sure Manny has any courses that we launch. I would expect we'll probably do new courses in early 2022. We're doing a winter program for students at historically Black colleges and universities this winter. So we're working on a variety of undergraduate initiatives, and we'll make sure you all know of them. Like I said, we will, one of the things that most folks could participate in the early new year is hopefully this undergraduate network with students from across the country. We'll have networking opportunities, so you can meet students in Maryland, in North Carolina, in New York, in California, Berkeley, whatever. So you all can meet one another and exchange resources, share advice, and really just start to actually build across universities, across states, the community of interested undergraduates in quantum. Sergio, email me if you want to talk. Cool. Any other questions? Otherwise, kudos to you all. It's not an easy thing to take on. Kudos to Manny for really starting to bring folks together and provide opportunities to learn this. But I'm here to be a resource. I live in the South Loop, so it doesn't take me long to get here at all, and I would love to stay in touch.
All right, for everyone in the Discord right now, I'll post the link to the recording in our general chat. The past 3 weeks of club meetings will also be posted as well, so I'll post links for that. For people watching online, the recording itself, in the description will be all the the documents we referenced, and all the useful stuff will be in the description itself. See you guys next week. I know you can still hear me on the audio, but for QubitXQubit, I know a lot of people, and I know a lot of people in the quantum community as well, and they've all spoken pretty highly of QubitXQubit. So, the community likes it too. I'll say that.
Thank you for the advice.
Yeah.